Okay. Okay, so the paper that we're going to be talking about today, well, for everyone who is new, my name is Carlos, I work at nPlan, we are organizing these meetups. nPlan, right, show of hands. Yeah, so we all work at nPlan, and if you want to know what we do, how we do it, and so on, you're more than free to approach us in the end, and we'll talk about it, okay? So, the paper that we're going to be talking about today is about open set deep networks. So, an open set, the main problem that this is trying to tackle is that machine learning models, they assume a priori that you know all the classes that you're going to encounter out there in the real world, okay? So if you're trying to classify 7 different things, your network knows how to classify those 7 different things, and that is what we call closed set recognition, okay? And of course this comes at a cost, which is that your network will always give an estimate for the output for any of the classes. So how do you know if the class that is being presented is nothing like what the network actually saw during training? So there are ways to do this within networks, and the most typical thing is do uncertainty estimation on the softmax output, which is basically if you do not have, so if your softmax output, so let's say that you have a network that's trying to classify 3 things, right? And your softmax output looks something like that, very, very flat. That means that the network did not produce high activation for any class. And then you can say, well, this is an example that is not known, okay? So that's what's called uncertainty thresholding, and you can define a threshold here. So if no activation goes above this, then you reject the example. But that is a very strong assumption that any example that you did not see in training is not going to produce a high output. And the chief example that they give in the paper is what they call fooling images. So a fooling image, which you can see here, is an image that is designed to produce high activation for the softmax, okay? Even though it looks nothing like anything that the network would know how to recognize. So the other approach that is somewhat traditional is to include a different class. Okay, so you include a 4th class, which is classified as unknown. So if you say this is my class target 1, target 2, target 3, and that one we call it unknown. And then you will produce an activation for unknown as well, and then you can feed it during training stuff that you don't want to classify. So if you get a high activation for unknown, then you can say this example is not known, and it is nothing like what this network was trying to recognize. But the main limitation here is that this relies on the known unknowns. Okay, you have to know what the network cannot classify, and there is no way that you can put every possible unknown into your training set. So the question is, how do we classify how do we detect the unknown unknowns? So everything else that is out there that the network is not trained to classify. And well, that's what this paper is all about, is to produce an alternative to a softmax output, which they call OpenMax. And well, they take a bit from extreme value theory, and we were speaking about it before. The interesting thing about extreme value theory is, so instead of, if you know the central limit theorem, which says that the mean value of all distributions is going to have a Gaussian distribution provided that they are IID and that you take enough samples and so on. The extreme value theory is concerned with the limits of the distribution. So if you take the maximum that a variable can take, and you think about how is that distributed given certain assumptions, then the idea is that there's only a limited number of distributions that can follow. And here they use the Weibull distribution because empirically they put somewhere in a previous paper, they showed that not the last layer, but the previous to last layer follows a Weibull distribution. So the activations here in this layer, if you call that the previous layer, they argue that empirically it was shown that these activations, according to the classes, if you define a mean value for these activations, a mean value, the distance from that mean value is going to follow a Weibull distribution. And what is a Weibull distribution? So I'm going to just bring up Wikipedia here because it's the best source of information. Wikipedia. Okay. So Weibull distribution is a particular case of a generalized extreme value distribution. Okay? And the interesting properties that it has is that it's a heavy-tailed distribution. So if you think about, I want to detect an outlier, I want to say, as the point gets far from the value that is not outlier. So if you say this is my mean value for a distance, let's say, well, you have this just there. So as x goes away from your mean value or from your target value, you want the probability to be high that it is an outlier. Okay? So that is what you see here in the cumulative density function, is that you can make it very flat depending on these lambda and k parameters. You can make it very flat at the beginning, and then as the quantity goes away from your expected value or from your mean value, then it becomes the probability of it being an outlier is high. Okay? So that's what a Weibull distribution is, and it has very interesting properties. And the method to detect outliers. Okay. So now we'll see the method that they use to detect outliers, which is quite clever, in my opinion. So there are two steps here. First is what they call the meta recognition. Open set deep networks. Where are they? Okay, so it's here. Okay, so the first thing is that we have to understand what is this distribution. So how are we going to define outliers? And as I just said, they take the penultimate activation layer. So if this is a deep layer, this here is going to have a number of activations. So these activations, we're going to call them the activation vectors. Okay? Then, for every example that your network classifies right, you average the activation vector. Okay, so let's say you have 3 classes. You're going to have 3 mean activation vectors. So you're going to have mean of activation vector 1, mean activation vector 2, and mean activation vector 3, which are the mean value of this activation, provided that the network classified the example correctly. Okay, is that clear?
Mean value along classes, or like do you have one mean value per data point, or mean value per class?
It is 1 per class.
Okay.
So if you're classifying, if your output is 3 classes, you're going to have 3 mean values, and these are mean activation vector. Okay, so it's going to be the mean value of point by point. Okay, cool. So then we have the activation vector. Okay, they argue that the farthest that you get from this activation, from this mean activation vector, the most likely is that the example does not belong to that class. Okay,